We'll continue with section 7.5, okay, page 192. Okay, ensemble methods are actually not predictive models. They are so-called meta-learning algorithms because you need to give them predictive models to perform prediction. Okay, how does this kind of thing works? Okay, you will find that in the lecture notes you are told there are two kinds of ensemble methods. One are averaging methods. So averaging methods basically just construct many different predictive models based on the sampling of our data, okay, and then we can generate many predictive models. So when the new data comes in, so the new data will be fit into each and every of the predictive models. Then finally we would have for each, let's say we have 10 predictive models, so each one of them will tell us, oh, the answer should be this, okay, the answer should be that, and then we can perform majority voting. Okay, like out of 8 of them say it's class A, then okay, only 2 of them say it's class B. Okay, then we will just take class A. If it's a numeric value, then we just average out, right? Okay, because each of them will predict a different numerical value. We just take the average value. Okay, so that's why these are the so-called averaging methods. Boosting is more complicated because it uses the concept of optimization based on something called loss model, and we know a little bit about optimization when we learn the linear regression is not something simple. It's made simple because we are told that, oh, the answer of the linear regression corresponds to a certain kind of matrix multiplication. Okay, but we are never actually shown how mathematically these two types of things are the same. Okay, so boosting methods are far more complicated. Okay, so let's begin with the first simplest first averaging methods, right? Okay, called bagging, which stands for bootstrap aggregation. So I'm not going to go into reading this thing out. Okay, what I'll be saying is, what is bootstrap? Okay, so let's say you turn on your R now. Okay, I turn on my R and then I just ask for help. Okay, just help for sample, and then you can search for bootstrap. Okay, and then you would find that, oh, there is an example here telling you bootstrap is nothing more than so-called sampling with replacement. Okay, so what are sampling with replacement? Sampling with replacement, you can think of it as something like taking samples from poker cards. Let's say you have you want to take 10 poker cards. So sampling with replacement is you need to duplicate the poker cards into 10 sets, and then you choose from the 10 sets. So is it possible for you to choose 10 A's? It's possible, right, if you're lucky. Okay, so that is sampling with replacement. If sampling without replacement is going to be, oh, we have a set of poker card, we just take 10 from it, and of course we know poker cards, just a set of poker cards doesn't have repeating cards there, so it's impossible for us to take 10 A's. Okay, because there are only 4 different A's in the poker card. Okay, so we will find that bagging actually has sort of like being generalized, right? Okay, so bagging itself is sample with replacement. There are other kinds, which is pasting, random subspace, random patches. So subspace is actually you pick, because we have x1 until xp columns, right? Okay, so instead of taking all 1 until p columns, we can just take randomly pick maybe 4 of it, 5 of it, okay, something like this. Okay, so these are random subspaces. Okay, and of course we can mix, and then that's why we have all kinds of these things. And the Python implementation of bagging or random forest actually include all these kind of generalizations. Okay, but the original bagging does not involve all the generalizations. Okay, so you have to be aware of it. So what kind of questions could be asked on these kind of things during test or an exam? It has to be conceptual questions, right? Okay, like SOA exam question 12 mentioned here. Okay, so you are asked to determine which one of the following is true. So A is linear regression flexible approach. Flexible means it can adapt to many different cases and perform right prediction, but linear regression is actually linear. Okay, the non-linear data distribution can't be fit, so it can't be flexible, right? So it's false. Lasso is more flexible. Linear regression is not true. Okay, apparently Lasso is actually a generalization of regression, so it actually makes add in some kind of measurement, okay, to the loss function, okay, something like that. So apparently it's false. So bagging is a low flexibility approach. It should be false, right? Because it improves the flexibility, because why? We have many different predictive models inside bagging. Okay, not just one predictive model. Okay, there are methods that have high flexibility and easy to interpret, right? Okay, this you should know that is false. Why? Because we mentioned it during topic 1. Okay, there is a diagram there telling you that, oh, if it's flexible, okay, then it's most of the time difficult to interpret. Okay, you can think of it something like non-linear function. Is it easy to interpret a non-linear function? It is not. Okay, but linear functions would be easy to interpret, because either it's increasing or decreasing, okay, something like this. So that's why the answer is E, right? Okay, so next, random forest. What's the difference between random forest and bagging? You can think of random forest as a generalization of bagging, because random forest, when we create the tree, instead of performing bootstrap sampling, we would limit ourselves to select m columns from the data. Okay, so let's look at the algorithm. So okay, so here it tells us we also use bootstrap sampling, but we are not actually taking from all the columns. We are taking from some of the columns. Okay, so we generate trees which is trained based on some of the columns are being removed. Okay, so So how can we actually see this in a programming environment? Okay, so you can find a lot of implementation, like this website, okay, provides a random forest implementation, and it uses what? Okay, you can find ID3 there, right? Okay, which stands for the ID3 algorithm I mentioned before. Okay, so these are just some kind of okay, line, how many, 5 until 4, wow, 51. Okay, they are just constructing the tree based on the table. Okay, it's just like in the previous one of the previous video, right, where I told you, oh, tree algorithm takes a data table, okay, try to transform it into a tree. Okay, and based on the tree, we can turn it into computer programs so that it can make decision for us. Okay, like this, right? Okay, the prediction, it's just you just traverse through the tree, okay, and then finally you can return a result. Okay, the implementation on the internet, okay, the one given here doesn't quite work, because I discovered there's some the return value, there are some problems to it which cause it to fail. Okay, train test split is something that you have seen in scikit-learn. Okay, for those of you who have used stack shape test or something like that, okay, that package also splits the data for you, okay, as yeah. So now you can find that random forest train, okay, just takes in the data set, and you have to tell it how many number of trees for it to generate. Okay, so you will find that it basically randomly samples. Okay, you can see data set sample here, right? Okay, just like what I told you there. Okay, sample with replacement. Okay, and then apparently this thing seems to be like a simple bagging. Okay, the implementation here seems to be like a simple bagging. Okay, others are just okay, here is just calling all these things and then perform calculations similar to your R. Okay, so what kind of questions that would come up related to this? Again, as I mentioned many times, right? Okay, it can only either conceptual or philosophical, asking you which of the following statements about random forests are true. So number of predictors used in each split is equal to total number of available predictors. Result is same or as using bagging. Apparently it's true. Okay, when building a specific tree, okay, yeah, the same subset of predictor variables is used in each of the split. So this is false because a new subset of predictor is selected for each split. Okay, so this is the crucial difference. So not too sure about the implementation here. Okay, so maybe you can have a look at it and let me know. So I think the implementation may be lacking a bit, because for random forest, right? Okay, if we have p features, okay, so m would be the number of features selected at each split. So we actually have another parameter called m, which selects only m columns. M is normally less than p, right? Okay, when m is exactly equals to p, and because the sampling is still the same bootstrap sampling, so they are the same. So that's why 1 is true. Okay, you can see that random forest differs from bagging by setting m less than p in general. So if you set it to be equals to p, it's just bagging. Okay, and there's some probability related to it. So it's true, right? Because then you reduce, you choose less columns. And yeah, typical choice is it p? Oh, okay. It's actually square root of p, okay, or p divided by 3. Okay, boosting, the most complex kind of ensemble learning methods. So why is boosting so complicated? Because as I mentioned just now, it uses optimization, and optimization is a very complicated thing because we are not averaging the output of our. Okay, just now I mentioned about bagging this way, right? Okay, we have 10 predictive models inside it. Then each one of them will predict some kind of output. Let's say 8 of them say A, and then 2 of them say B. So based on majority votes, we will take A as the final output. Okay, but in boosting, we can't do it like this because boosting requires to wait. Okay, so let's go to the algorithm mentioned here. Okay, what this whole algorithm is saying is this. Okay, we have 10 predictive models. Okay, we need to give them each of them a certain weight. Okay, and then we need to adjust the weight by checking on the. We need to introduce something called a loss function or error, square error. Okay, this kind of concept, and then we find that okay, the one with more error, okay, then we should train it more so that it generates less error. Okay, and then we start to modify. Okay, so some of this part here is okay, based on some formulation. Okay, change the weightage, okay, depending on how well each of the predictive models behave. Okay, if the score is high, okay, then probably it's maybe just to be lower. If it's low, then it needs to be trained more. Okay, and finally, okay, then only we try to average out all the predictive models based on certain weightage. Okay, so the key difference with the averaging method is averaging method just treats everyone equally. Okay, here things are adjusted. Okay, so that's the main difference. And of course you'll find that it is a large set of algorithms. Okay, because in R there are so many different packages, each with its special strength. Okay, some of them are simpler. So what can I say in the end? I can only say, okay, the flexibility is more or less goes like what is shown here. Okay, boosting is always more flexible than random forest, and random forest is more flexible than bagging, and it's more flexible than a single decision tree. Okay, however, okay, a bit of warning, don't always use the best thing, because is, how should we put it, okay, when you need to solve a simple problem, you don't need a complicated mathematics. Okay, if it's just solving ax plus b equals to 0, you just need simple arithmetic. So we always start from the simpler predictive models. Okay, if that's not sufficient, then we start to go up. Okay, find a more complicated predictive model. Okay, so boosting, random forest, bagging, all these ensemble methods, you can think of them as taking many generating many predictive models, put them together to form a super predictive model which can do things. Okay, super predictive models, despite its power, takes up more resources, takes longer time to calculate. Okay, so do beware. So I think for the next class, I'll go into the examples first before we go into the practical, because I mean, some of you have actually used random forest tree methods in the assignment already, so playing with it seems something like it's not a problem for you. So what is important is actually, you need to know what is roughly, okay, just roughly going on, okay, by looking at the calculation. Okay,